Right, welcome back everyone. Um, so what I intend to do is show a whole lot of examples of how HyLogger is used, most of them to do with alteration geology, some not. And I'm going to do it by looking at what the effects are on spectral behaviour. So it's sort of taken from a slightly more technical point of view. But as we go through this, we'll touch on all sorts of things, alteration. Okay, on with part two. So shortwave infrared has been used for mapping hydrothermal alteration since the 1990s, I guess, where, as we've seen from elsewhere in the course, there's an alteration zonation from core to periphery to far field can be seen in the mineralogy, and that's reflected in the spectral geology as well. And so, although the names may be very different, actually eyeballing the difference between these rocks that are characterized by these minerals can be difficult. And if we want to see that the changes in proportions are in these minerals, then it gets even harder. So all of this can be identified firstly with the HyLogger, and secondly can be quantified. So we can say how much alunite compared with kaolinite. Is it increasing this way or this way? Are we getting closer or further from the core of the system? Okay, so the carbonates are useful in that we can look at the actual carbonate species and the ratios of them. They've all got quite different spectra. So the core of a system might be more anchoritic than the periphery of a system, which might be calcitic or dolomitic, and so we can use the characteristics of the carbonate to fingerprint that. Same with feldspars, the various feldspars, K feldspars and Pager K feldspars can be used as in vectoring towards core if you've got a system in which that is the case. I'm just going to have a look and see if there are. So a typical purpose for the shortwave infrared, the absolute classic is fingerprinting the composition of the white mica using the feature, which is located at 2200 nanometers, which is moves from short to longer wavelengths as you go from aluminium rich to iron, magnesium, silicon rich. And the calibration, it's not perfect. So we really do rely on the power of oversampling of the HyLogger to sort this out. If you have 5 samples which are increasing in going from muscovite to phengite, and you did the spectral analysis of them, they might not do anything sensible. But if you had 50,000 samples where there was a trend in one drill hole, number of drill holes, then you would see that, just because of the sampling is completely oversampled, and the calibration statistics like this just pale compared with the trends that you see. Chlorite is the same. We can calibrate the Mg number. So this is Fe chlorite and Mg chlorite, and there's a correlation, and there's just a few data points showing that the wavelength of this feature varies with the composition of the chlorite, and with lots of samples, significant trends can be seen down drill holes. The kaolin group, we can look at the crystallinity from poorly crystallized to well crystallized. So before we were looking at the composition of minerals, here we're looking at the crystallinity, which varies. You can see that the amount of water, this feature here varies, and the details of the absorptions. There's a doublet here which comes and goes and varies depending on the crystallization of the state of the kaolinite. For instance, here at Rockley Dome, the poorly ordered kaolinite occurs in the cover sequence. This is a paleo valley here, and below we get the the well-ordered kaolinite in red, so that each drill hole goes from poorly ordered and transitions to well-ordered as you go down the drill hole, delineating the bottom of the valley, which would otherwise be quite difficult to see. I mentioned water in the first part of the talk. The spectrum for water is actually rather simple. And so if you have a spectrum that looks like this, it means you're only seeing water, but you're looking at a rock. So where's the water? It's probably just in quartz. And we can use that feature. So here's a dry kaolinite compared with a wet kaolinite. And we can see that the only real difference, the main difference, is that these water features are enhanced in the wet kaolinite. So the wetness of the sample, it's not really wetness, it's how much water is in the crystalline structure, either loosely bound by adherence or in between the crystals. It's not, if you like, structural water. Can be measured or by seeing what sort of spectrum it's more like. Okay, and these things will vary down drill holes depending on what you're looking for. So we might expect the dry kaolinite to occur in a more evolved, deeper part of the basin than wet. There are particle size effects. Usually, the smaller the particle size, the better the shortwave infrared spectra. But on the other hand, the thermal infrared spectra don't do so well. So RAB chips, for instance, although you can do TIR spectral analysis on them, it's not so good if they are really fine grained. So there's all sorts of grain size effects. The grain size effects will affect the transition from being mainly reflective, or the light coming in and then out of the crystal in the shortwave infrared, and then as you go into the thermal infrared, the light doesn't actually get into the crystal at all. But at fine grain sizes, the light will tend to get into the thermal infrared, will tend to get into the crystal as well. So luckily for us, most drill core, most rocks aren't too bad. Fine-grained shales can be very non-reflective. Mineral mixtures are interesting. That we can use the magnitude of the spectral features to correlate with abundance to a degree, especially if we calibrate it. But the system really is characterized by non-linear mixtures, so that the magnitude of spectral features are normally not correlated very well with abundance. I'll show you here. So here's a mixture of jarosite and eleonite. So eleonite's in the blue up here. So that's the spectrum for an eleonite. And the red is the spectrum for a jarosite. Okay. So if you mathematically mix the two together, you get this dotted line. It's just going to be halfway between the two. Okay. That's what we think if we did a linear calculation, what the spectrum would look like. The actual spectrum, when you mix 50% of these, is this green one, which tends to follow what we might predict in a linear sense in this area, but out here the spectrum is actually dominated by the jarosite. We don't see the eleonite at all. So that's what I mean by non-linear mixing effects. Yeah, so it's when we unmix a spectrum, an unknown one, say the green one, into proportions of two end members, that say minerals that comprise it, the eleonite and the jarosite, we probably won't get it bang on, okay? But we will see trends. So examples of all this sort of stuff now we'll see, and we've got a whole lot of things which are mainly geared around exploration, but there are some others. We see systematic spectral shifts. Okay, so the anhydrous silicates, you can see that a typical spectrum of quartz here has a spectrum like this, and then as we go to more mafic minerals, so here's the list up here, so from quartz to microcline to albite to muscovite to, I can't read that one, down to hornblende, diopside, epidote, and down to garnet. You can see that the spectra tend to shift to longer wavelengths. So when we go from top to bottom here, we're actually going from felsic out to mafic. Here we are, the equivalent thing here. So a felsic granite has a spectrum like this, which is dominated by quartz, and a dunite down here is a spectrum dominated by pyroxene. And so if we were to measure the general shape of all these things and call it a felsic, some sort of scalar, felsic mafic indicator, it would increase as we go from here down to here. So that's just a basic mapping tool. So a simple scalar that just does a broad brush estimate of what this shape looks like can give you an indication of how felsic or mafic a rock is. And here's an example. The felsic mafic index is another one called the Christensen minimum, and they're both in TSG, and it maps the peak wavelength of that reflectance curve in the TIR. So here's a skarn in Tasmania, and we can see that we get bumps all the way along here, which are telling us changes in the felsic mafic nature of the rocks, probably related with the protolith in this case. And as I said, so when we have short felsic mafic index, we've got things which are rich in quartz, and longer ones is where the amphibole is. So it's a general way of mapping out mineralogy of the core without actually looking at the minerals themselves. Going on with that Mount Lindsay, here's the geologist's log of a drill hole, showing the proportions of minerals. So this is the pyroxene, garnet, pyroxene green there, and then I think Vesuvianite in this colour, pucey colour, and plagioclase, and this is the amphibole in the dark brown. Okay, so it's kind of a mixed thing, and this is what the HyLogger produced and validated by XRD, and you can see it's a much cleaner result in the HyLogger. What the HyLogger did produce, it's interesting that the geologist log really did focus on the alteration minerals, as if the geologist was kind of focused in on those, and it underrepresented things which were just in the background or protolith or unaltered mineralogy, whereas the HyLogger was more objective and it could see all of that. So it's just getting over, if you like, biases that we have as geologists that are quite difficult to get around. You know, we just like the shiny stuff, I think. Going on with this Mount Lindsay, we can use the hyperspectral data to map out zonation, mineral zonation. So here we have quartz as increases as you go away from the centre of the alteration zone. And there's a zone of amphibole and plagioclase, calcium garnets in towards the middle. I think the next slide highlights this, so you can see the zonation. We've got two types of amphibole, which become as we move towards the core of the system, become more concentrated. Prehnite down here, carbonates and axonite in the core of the system. So there's the mineralogy straight from the HyLogger is showing us the zonation, which we expect to see in the skarn. Here's Henty looking now at the composition of the white mica. So that composition is shown in blue, and for 3 drill holes into the Henty deposit down here at Mount Julia, we can see the wavelength of the white mica is fairly constant, and then it wobbles around a bit, and it takes a big dive as we go into the alteration zone. So, and the intensity of the white mica in the pink is variable, but it can be increased at the edge of the most altered material as well. So this is characteristic of many VMS and other deposits, that the white mica composition changes. In this case, it's going down as you go into the deposit or into the more intense alteration. At Hellier, it goes the other way around, and you get to more phengitic white mica as you approach the ore. At Glen Lyle, it's the same thing. We have low wavelength white micas associated with the alienated core of the alteration system. Here it's surrounded by a pyrophyllite, and then low wavelength white mica, possibly paraganitic, and then more muscovitic white mica outside that. So these things have been interpreted. I think we have one more here with the interpretation of Mount Sedgwick. This is an uneconomic system, but we can see the white mica wavelength dropping away into the core of the system and bouncing back out here. And then there's pyrophyllite in the middle of this. And this, Scott Halley came up with the idea that this is just mapping basically the pH of the hydrothermal system, with muscovite, the low wavelength white mica aluminium rich, being more characteristic of low pH, and phengitic being of high pH. But there are other variables which can contribute to this as well, which are probably underutilized at the moment. There's plenty of scope, but there's one variable, pH, which may contribute to this. So, and I think Scott advocates that at Henty, the actual deposit is at the zone where a low pH and a higher pH mineralogy, reflecting fluid, have mixed. Up in northeast Tasmania, we have a similar thing. We're showing the white mica wavelength in brown here in these drill holes, and on some faults it drops away very sharply here, like here, and other faults it doesn't. And only the faults that have the white mica wavelength decreasing a bit across them are the ones where we have gold. So it really is tracking the prospectivity of the fertile faults in the area. Now the wavelength difference we're talking here is only 2 to 4 nanometers, which is really small. And if with a handheld instrument, you might get samples which show that, but you just don't have the power of statistics to tell you. When you have, again, 50,000 samples down a drill hole, you can see that change. You've got plenty of background, and you can see the change. And so 2 to 4 nanometers is detectable and reliable. And I think we've seen similar things happen in Bendigo, Ballarat, on the mainland. Kanana Bell, here we're looking at this white mica chemistry. Note it's not telling us so much here, but the carbonates, the ore zone here, it's covered by gold. So the gold is in this area, and it's characterized by the carbonate being dolomitic. So that dark reddish color there is the dolomite, and the dolomite is where the gold is. So once you've, if you like, calibrated that information using a HyLogger, you can use a handheld instrument or other ways of finding out where the dolomite is, and that ends up being a shortcut to finding the gold. At Olympic Dam, I think Alan Major did scan 20,000 meters of drill core and came out with basically 14 data points. But the data points were important. You can see that the white mica composition varies. This is the average for each drill hole, so there's thousands of instruments here. The white mica wavelength kicks up as you go into the ore body, but you can see it's all inside the 5% contour, 5% iron contour at Olympic Dam. So it's telling you where you already know the ore is, and the same with the chlorite composition. But we get a much, much bigger halo if we look at the feldspar. So plagioclase abundance, which is in the black here, makes it as a very wide halo where it's the plagioclase is low, and the K feldspar might have a similar trend as well. And you can look at the mineralogy of those minerals as well. So a much broader halo was found using the plagioclase and K feldspar. But boy, an awful lot of work. There's a lot of samples. He got a medal for it. So it's a big achievement for Alan. Here's what looks like a pretty boring rock. It's Tasmanian dolerite, and I'm looking at the pyroxene composition here. So there's an estimate of the amount of iron and calcium in the pyroxene, and there's some variation here down the hole. But when we look at it close up, here we've got a tray view. The proportions of the pyroxene, of the composition, of the pyroxene varies as we go down, and so it changes on a scale of tens of centimeters. And these are banded dolerites, which you can see when you're in a cliff, when the things are kind of weathered. But when you look in core, it all looks the same. You can't see it anymore. It's very cryptic. And the only real way to see any of this would be to put a portable XRF hundreds of times down this tray, for instance. But the HyLogger, we can see it all straight away. So potentially, this is not an economic lithology, being dolerite, but it's it just flags the idea that an otherwise boring rock can have subtle changes in mineralogy which can be brought out using a HyLogger, for instance, this sort of a view. Here's this is a otherwise difficult to interpret stack of basalts, the beta basalt in the Olympic Dam cover sequence, and HyLogging it was able to identify all the separate individual basaltic flows in here just by mapping out the pyroxene abundance. So the pyroxene increases in abundance as you go from the top of the flow down to the bottom of each one. So lots and lots of flows here, but visually this stuff's very, very hard to pick up without it. So that's the benefit of those infrared eyes. Looking at carbonates, this is Rosebery, where the ore zone is characterized by rhodochrosite and kutnohorite, which is another manganese on the way to rhodochrosite carbonate, whereas most of the rest of the core is calcite in green and anchorite in brown. And in detail, there's a halo in here as well, with rhodochrosite in the core, and then ferric rhodochrosite outside of that, and kutnohorite in between. So, and this is much wider than the actual ore zone, so great indications of where there's ore in the vicinity. Another VMS deposit, we can see that this is a classic Mount Reid volcanics hole through a whole heap of sandstone and then shale with the limited shortwave infrared reflectance down into felsic volcanics here, characterized by a change in the ratio of muscovite to chlorite, or the chlorite cerussite ratio. So these are easily seen using the HyLogger. So in that hole, there's we can characterize the carbonates using a couple of spectral indices, the wavelengths of two of the thermal features, and we get all the carbonates are in this sort of space, but we can characterize them spectrally, and these colors have been determined using spectral techniques. But when we look at typical images of each of these populations, we can see they really are quite different. The rhodochrosite here is a spotty thing in the background. Up here, the calcite typically occurs as veins. The anchorite and Fe dolomite occurs as some sort of banding through the rock, and the dolomite is this sort of microveined material. So we can pick out the textures that way, but it was all originally done using spectral geology. These sort of textures are very hard to pick up just with your eyes. Once you've got your eyes in, by using an analysis like this, it's very easy to see the populations of carbonate, and you can use that information to go and map as many drill holes as you like without having to go and HyLogger them. So here's those, using that information about the carbonates. Here's the a downhole histogram of the carbonate population. See, it's dominated by calcite in green, but if we remove the calcite, the trace, if you like, carbonates are dominated by dolomite and anchorite, all this part of the hole, and then rhodochrosite down this part of the hole, which is the juicy part of the hole. So that's again, it's the rhodochrosite that's telling us where the goodies are. Queen Hill on the west coast. There's a deposit near Zeehan, Zeehan town centre, and I think the golf course is under here somewhere, over that top of the Severn deposit somewhere. I might not have that right. Anyway, it's right near the centre of town, and I think cross section. Yep. So there's some drill holes. And the HyLogging, we can map the mineralogy down the drill holes and put in some map on the different carbonate compositions. So here it's calcite and anchorite, siderite in the core of the system. This red colour here is the ore system, and then going down to dolomite beneath it. So again, the carbonate, even though it might only be a minor part of the rock, can be very indicative of a lot of the hydrothermal action going on, and are easily picked up by the HyLogger, but quite difficult in the field. And because these things are a minor part of the rock, maybe not so easy to see by the geologist in logging the core either. And by the by, this is mapping the wavelength of the chlorite in the system, and we have high wavelength iron-rich chlorite in the core of the system, zoning or grading out to lower and more magnesium chlorites as we go away from the center of the system. Again, not something you can see visibly at all, of course, it's entirely chemical. Mineral proportions, we can calibrate. As I mentioned, here we're calibrating the amount of gibbsite in a mine-based deposit where they didn't want gibbsite in the ore, so they could use hyperspectral techniques to actually calibrate that. Characterizing regolith and cover, here we're at Prominent Hill, and it can be very hard to tell what's regolith, what's cover, and what's bedrock, but with the HyLogger, I won't go into the details here, but we can see the general nature of these plots. We can characterize the different types of cover, 3 different types of cover, and the bedrock quite easily. And these are typically done by measuring kaolinite, illite, that sort of thing. Cooper-Pedy, at opals, we're mapping here in high density the amount of montmorillonite, gypsum, kaolinite, and alunite. And where this alunite is, this boundary here is like the bottom of the paleo water table, and that's where the opal occurs. So here it is mapped out, and you know, this is like the silver bullet for finding opal. Mind you, there's a lot of drilling here, isn't there? But it's easy to drill through, isn't it? So you can imagine what this looks like in 2 dimensions. You're just mapping up the paleo water table and mapping where all the best opal is going to be. Looking at dolomite, this is in northern Tasmania, a rock, a sequence here, 1100 metre drill hole with drilling down into Neoproterozoic snowball earth dolomite. And the composition of the dolomite is indicated by the wavelength of a particular carbonate feature. You can see it splits into 2 here, so there's 2 sorts of carbonates running in parallel because there's 2 wavelength features. And there's interesting bits down here. If we look closer, down here we can see gradations in composition which are indicating either alteration or the protolith carbonate variations in it, showing us probably original reef sequences. Here we are in New Caledonia. We're going to be looking at the same thing. We've got a lot of carbonate in a fish sequence, and there are the strength of a carbonate feature, or the height of that feature, and a wavelength of another carbonate feature. They map out how fine-grained the material is. So I can use the characteristics of the spectra to map out the grain size. We can show that here. This is the one of those features, the 1100 wavelength. And we can see gradations. These are going to be finding upward sequences in the fish. These are, you know, a shortcut to mapping these things without meticulous logging. Carbon capture, we can, I think here we are, Harvey, a test hole, looking for aquifers and aquicludes. And we can see down the drill hole, we can where there is poorly crystalline kaolinite compared with smectite, and then well crystalline kaolinite are going to map out where your aquifers are with the well crystallized kaolinite, and where the montmorillonite is going to be the aquicludes. So lots of juicy stuff here. I think this is the final one now. This is looking at this tiny little spectral feature here, which is the leftover of chlorophyll. Turns into something called chlorine, and chlorine has a spectral characteristic here. So the magnitude of that feature, or the depth of it, is going to tell you how much chlorine, and maybe how much chlorophyll there was laid down at the time. And so the amount of chlorophyll might be related to the amount of autotrophic plankton productivity. And so where you've got a large number up here, it might have been, there's a lot of plankton, may have been warmer. So when we plot this up, we can actually correlate it with paleo temperature ocean records with warming dark ages. So this is only 12 meters of core, but I've calibrated it by sedimentation rate, and just plotted the depth of that feature, and it gives us a sea level temperature record. You can predict rheology if it's related to the mineralogy simply by getting the mineralogy out of the HyLogger and then calibrate it. Petroleum exploration, you can see petroleum directly in the spectra. I've not done it myself. And we can combine spectral data with other logs and see most of these other logs, this gamma, mag-sus, most information is actually from the HyLogger. Finally, 1 minute on where you get all this information from, the NVCL. This is the data access either through the Oscope or through the OSGen, selecting the National Virtual Core Library and turning on all the nodes. You can get pictures of drill holes, you can look at analyses, and you can download entire data sets from Mineral Resources Tasmania and other agencies, state agencies. You can go and use their own databases to try and find which holes have been HyLogged. So I think we've done 450 odd in Tasmania, all over the state. So we've done 11% of our core library. We'd like to do 100%, but we're actually getting more core in. The core is coming in at a greater rate that we can scan it. So we are probably going to stay at about 11% for some time. We've done 124,000 metres, 124 kilometres of core. I think the nation's done something like 20 times that. So there's a lot of information out there. All right, there's a quick rush through some applications of hyperspectral logging for part 2. Just emphasising again that HyLogging is objective, consistent. We've got that incredibly high oversampling, minimal sample preparation. That's semi-automated interpretation. And it gives us ideas of porogenesis. We get lots of spatial trends. We can use it for calibrated mineral proportions, and there's national remote access digitally to all this data. Okay, that's me done. Thanks for listening. I'm not sure if I'm around for questions or not. Back to the boss.